Hello and welcome back to the Science of Concrete Materials class. This is lecture number 3, and today we are going to start talking about the cement module of the class. This module is a bit large and is going to take several lectures to cover. So let's see what we will be covering in this module. First, we are going to define what is cement. Then we're going to have historical perspective, see how cement developed over the years. Then Portland cement manufacture, how is Portland cement manufactured, Portland cement composition, the cement types, the tests performed on Portland cements and also on the pastes and maybe mortar. We will go over the cement hydration process in detail. We will look at the hydrated Portland cement microstructure and the structure of the concrete. Then we will cover the supplementary cementitious materials and also blended cements after that. Okay, so today's lecture we are going to define what is cement and look at the historical perspective. So first, let us define cement. The general definition before we get into Portland cement. Cement is a material capable of binding particles together. Portland cement, which is the focus of this class, is a mixture of calcium silicates and aluminum silicates that react with water to form a binder. The Portland cement, as I mentioned previously, is a generic name and not a trade name and has nothing to do with Portland. The modern Portland cement was invented in the 19th century, but the related materials have been used in construction since at least Roman times. So let's see how cement developed over the years. As far back as early Egyptians, 3000 BC, the early Egyptians, they calcined impure gypsum according to this equation you see here. Then after that, the calcined gypsum, which this is the resultant product right here with and water, when this material, is mixed with water, the small quantities of water, the setting of this material basically is due to the recombination of the calcined gypsum with the water of crystallization that has or had been driven off during the burning process, as you can see here. So this material, basically, they use the gypsum instead of lime because it required only, relatively low burning temperature, something on the order of 130 degrees Celsius. So these gypsum-based mortars are non-hydraulic, that is, hardening will not take place underwater because gypsum is quite soluble. Okay, then after that, let's go back. After that, Greeks somewhere around 600 BC, they used calcium carbonate in a process called calcining. Okay, according to this equation. Basically, this calcium carbonate is a rock, is heated to around 900 degrees Celsius. This, will result in quicklime, which is the calcium oxide. This right here. By driving off the burning process, basically drive off the CO2 from the calcium carbonate, and we end up with what's called the quicklime. Again, at reaction with water, this quicklime will form a product called slaked lime. This calcium hydroxide. This is a slurry material, basically. So this lime plaster or lime plaster is made by compacting slaked lime on a surface such as a wall or a floor, or can be used to glue stones together and allowing it to react with the CO2 in the atmosphere to form calcium carbonate. And again, according to this equation, the slaked lime will react with the CO2 in the atmosphere, will result again calcium carbonate in solid, and of course water driven off. As it dries, it gains strength. This is an artificial stone, and but unfortunately this product is not stable in water, so it is a non-hydraulic cement. So again, the need still existed for a cement that is stable in water. So the ancient Greeks at some point in time reacted slaked lime with with volcanic ash, mostly SiO2 glass, glassy silicon dioxide, to make cement to line cisterns and some water holding structures of that sort. This material basically is the precursor of modern cement. From about 200 BC, the Romans developed cement technology based on slaked lime and volcanic ash they obtained from Mount Vesuvius. They reacted basically quicklime by, of course, calcining limestones, as you can see here, and heating this with reactive silicon dioxide, which they obtained from volcanic ash, to produce some type of calcium silicate, according to this equation, of course, with heat. The exact chemistry of the formed product, this calcium silicate, was not known. As you can see, it's denoted by X and Y because we did not know what the exact chemistry. Anyhow, at reaction with water, this material formed some type of calcium silicate hydrate product, according to this equation right here. Okay, this what is actually responsible for the strength in modern cement. We refer to it as calcium silicate hydrate gel. We will get into the definition of it a bit later. Okay, so let's talk about this reaction here. You can see here. This reaction, as I said, is what is responsible for the strength that we get from hydrating cement. So where did the Romans get the volcanic ash? The best source was Pozzoli. That's where the name pozzolanic reaction came from, as we will see later. This ash contained reactive silica, not crystalline, reactive silica. So with the development of this material, Romans were able to build a really impressive and lasting structure, starting in the 1st century AD, such as the Pantheon, the aqueducts, and Colosseum. These structures we still see today. The Roman concrete, had great advantages. It was strong and easier to use than stone, for making smooth shapes such as domes. It could also set underwater, so it could be used for piers and pediments, bridges and the aqueducts. This is what the Romans used to provide water from a distance for their cities. The Roman concrete, however, had some disadvantages. First, it takes a long time, maybe up to a year, to reach high strength, so the structures can sag before fully hardening. And again, the raw material, which is the volcanic ash, are not widely available. So in faraway places, it has to be shipped from Italy to the faraway places in the empire, which was not really very convenient. And again, the variability of the mined volcanic ash caused this concrete to lack uniformity. After the fall of Rome, however, concrete technology unfortunately was lost in Western Europe until sometimes in the 19th century. Okay, this is a photo of the Pantheon. Shows you some structure like this was built in the 1st century AD. That's very impressive. Okay, so let's talk about the rebirth of the cement. The need for hydraulic cementitious material developed again in Industrial Revolution Europe. In 1756, John Smeaton, which is a civil engineer, was commissioned to build the Eddystone Lighthouse off the Cornwall coast in England. Since contemporary mortars would not set underwater, so he experimented with various local limestones. When limestones containing clay were fired, the resultant lime gained strength underwater. However, the silica was probably present in the form of kaolinite, which is less reactive than volcanic ash, which means more energy was required to produce the calcium silicate, which means more expensive. The formed calcium silicate from this process was mostly present in the form, believed in the form of C2S, which is dicalcium silicate, or the belite. We will talk about this later. This is the mineral, as I said, we will discuss later. It gains strength slowly. And again, that was a disadvantage. This is the Eddystone Lighthouse. Again, in 1824, Joseph Aspdin, which is a British mason, patented Portland cement. This was named so because it was said to resemble Portland stone, a high quality limestone quarried near Portland, hence the name Portland. He made this by firing clay and limestone, but evidently he did that, at too low of a temperature. Okay, it is said, his formula did not work and the product did not gain strength as he advertised for it. So maybe he was a better salesman than a cement manufacturer, but that was the case. After that, in 1840, Joseph's son, William, solved this problem, basically by using larger amount of lime, calcium oxide, and fired the feed at a higher temperature, and ended up probably with what we call today tricalcium silicate, or alite, according to this equation. It is believed, he heated the feed up to 1800 degrees. So he ended up with this this phase, what we call tricalcium silicate. And this is really the building block for modern cements. In 1845, Isaac Johnson made the type of cement now known as Portland cement. Basically, he fired it at a high enough temperature, maybe on the order of 1500, to make highly reactive calcium silicate. Okay. Again, just to re-emphasize, the reactive calcium silicate, it's what reacts with water and produces the calcium silicate hydrate gel, which is responsible for the strength gain. Okay, this is it for the definition and history of the cement, and next lecture we will talk about the manufacture of Portland cement. Thank you for watching, and I'll see you next time.